morning. Okay. No, yes. Hello. Well, good morning, ladies and gentlemen. It's a pleasure to have you back for this second edition of the webinar. As you know, my name is Mauro Giagnorio. I'm the sales manager at PAD Group for EMEA region. And PAD Group, it's a multidisciplinary group of companies specialized in the equipment manufacture, analyze, advise, and implementation of production projects and technological services. In this opportunity, as I said before, we're going to initiate with the second of 6 webinars, the wet granulation line. But before we start with this webinar, we will wait 2 or 3 more minutes so everyone can access to this session that it will be really, really interesting. Yes. Hello, welcome back, everyone. I can see that someone cannot listen to us. Can you please confirm that now you confirm? Okay, thank you, Mr. Ahmad Burhag, for your confirmation. And welcome again, everyone, for this second edition of the webinar. Thank you for this patience. So we got all the people can assist the webinar. Before we start with it, please let me inform you about the terms of this edition. As you know, the headphones will be shut down to avoid interruptions. And in case you have questions or comments during the presentation, we will proceed the following way. In the lower right corner of the menu, you have to choose the activities option and then questions answer button. It is the latest option. Once this question has been formulated, we will answer it during the intervals for this purpose. All the questions that we don't answer during the webinar, we can also do it by email. And in case you have further questions, you can also get in contact with us to our email, which is info@padgroup-sa.com. Well, it's already 11:04 here in Spain. So now, please let me introduce you the professor and pharmaceutical degree, Mr. Arturo Oya. He's in charge of this dissertation. Arturo is a very expertise pharmacist, very large experience in R&D and production area, and he has more than 30 years working in Vago Laboratories, which is a prominent pharmaceutical company amongst other. So for me, believe me, it's a really pleasure to introduce you, Arturo. A great benefit, and I will appreciate that you can listen him carefully for this exposition. So please, Arturo, now it's your time. Thank you very much. So sorry, Arturo, we cannot hear you.
I mute. Excuse me.
Yes. Now we can hear you.
Thank you, Mauro, for introducing me. And well, good morning and welcome everyone. And thanks for taking time to hear our second webinar about pharmaceutical technology of solid dosage form. I want to share with you the presentation. Let me see. Wait. Okay, I have a problem with this. Only 1 minute. Here we have. Okay, please let me know if you see. Can you see
Not yet, Arturo.
Oh, excuse me. Try again. Now?
No, not yet.
No, not yet.
Yeah, no,
Not
no, yeah. Okay, it's going.
No,
It's
yes,
okay?
you know.
It's okay.
Yes, yes. No,
Okay, thank you.
thank you.
Well, the wet granulation line, this is the webinar that we give an overview today. First of all, I want to remember that in the first webinar, we presented the three main lines used for produce the intermediate product, the product we put in the hopper of the tablet machine. Let's remember, we have this, the intermediate product is the lubricated blends of powders or granules to fit the tablet press. This slide is the complete line to produce tablet by wet granulation. In this webinar, we will see only 3 operations of this line. These ones: wet granulation, drying, and milling. The rest of the operation will be presented in the next webinar. Well, this slide shows the transformation of fine powders, the raw material, excipients, API, and the transformation when we apply the wet granulation in high shear. This transformation implies not only the particle size enlarging, a new particle shape, more density, and very important, the API, the active, bound to the granules. This is very important to avoid segregation. And other transformation occur when we make wet granulation in high shear. Well, the attributes that obtain, that reach the granules will define not only the quality of the tablet, but the tablet production speed too. So for this reason, it's very important that the intermediate product have a good attributes to produce quality and speed. What do we feed the tablet machine with? All machine, model machine, and can any intermediate product be processed by this tableting machine? For example, one intermediate product with reduced flowability and compactability only could be tableted in a low-speed tablet press, but not is possible in a high-speed machine. So, what attributes must the intermediate product have to be able to be tableting at high speed? High speed means, for example, 2,000 tablets per minute or more. So it is very important, this question, because we need to obtain the best intermediate product that be able to tableting at very high speed. 3,000 tablets per minute, 4,000 tablets per minute is the figures that today is possible to obtain. Well, here is a linear simulation of the tableting processes in high-speed production. When the intermediate product, look at this is a hopper of the machine. When the intermediate product is put in the hopper and flowed to the feeder, the main attribute that this intermediate product has to be is its density, its blend flowability, blend compactability, and blend uniformity. So high speed production and high quality product will be reached if and only if the intermediate product have these attributes. It's very important to be in mind this. The operation of the tableting will be presented in the webinar 5. So now let's start with the wet granulation process. This slide shows the two machines, the two types of machine, the low shear and the high shear. As we will see now, high shear granulation has a lot of advantage over the low shear. This machine is a high shear mixer granulator. This machine let us to not only granulate, but mixer powders too. Well, these are the parts. It's a section of the equipment, and here we want to show the the component and the function of the high shear granulator. Look at this. You have a bowl or container. This is very important because the shape of the bowl determines the movement pattern of the powder, and this movement will impact in the size, the enlargement of the tablet of the granules. The other component is the impeller. Impeller is this device that rotates at high speed, producing cutting, producing compaction force, and delivering the energy that the process needs to transform the powders in granules. Chopper is very important too, because reduce the size of the large agglomerates, the lumps that forms during the process. The solvent addition device defines the flow rate of the solvent and the droplet size of the binder liquid. This is an aspect to be in mind, because we need to control the flow rate and, if it's possible, the droplet size. Finally, the machine has in the shaft, mixer shaft, a device in order to measure the torque, the power that will give us the possibility to detect precisely the end point of the granulation. Here we show the process variable in high shear granulation. These are the principal. In red are the critical ones. For example, impeller speed is very critical because, as I said, gives the energy to transform. The granulation time is very important because it's critical to avoid the over granulation. And the flow rate is important because the flow rate and the droplet size could impact in the shape, in the particle size distribution, in the porosity of the granules. The most important variables is impeller speed. Impeller speed defines the level of shear and the energy transferred to the powders. So the quality of the granules mainly depends of the impeller speed. Of course, for each product formulation, the developer must find the value and the configuration, the condition of this variable, especially the variables, the critical variables. This is very important question too. Now, I want to show you a comparison between the process characteristics in wet granulation at low shear compared with high shear. Here we have the powder per unit mass delivery is very low or low in low shear, but is high in high shear. The process time is large in low shear. Let's suppose 60 minutes, 1 hour more or less. And in high shear, the process time is very short, 5-10 minutes, no more than this. The binder liquid consumption is high in lower shear and low in high shear. This is very important because then you have to dry less solvent. Liquid binder application mode, the mode in which we apply the binder liquid, is critical. It's critical for low shear, but not critical for high shear because the impeller is rotating at high speed. Applicability of formulation. Low shear have some limitation. For example, cohesive powders of hydrophilic polymers is very difficult to produce in low shear. And high shear has no limit in terms of formulation. Any formulation will function in high shear. Risk of overweighting, overgranulation. Well, here is another question. Low shear, the risk is low, but in high shear, the risk is possible. So take care with this, to be in mind that the risk of overgranulation is possible in high shear. The end point of granulation, in which moment we stop the granulation? Well, in low shear, hard to predict or unpredictable because we haven't devices to obtain this predictability. But in high shear, we have many sensors and the possibility to predict reasonably this endpoint. And reproducibility is another process characteristics that is low in high and low shear, but is very high in high shear. So we see that high shear has a number of advantage over the low shear. Now, I wanted to show you granules characteristics. It's, let's say, the product of the process. Well, size and shape of the granules when we make low shear is regular and very regular when you use high shear. Particle size distribution is low in low shear and very low. That is a good quality. Very low particle size distribution is a very good characteristic, very good attribute. Simple density or density, apparent density, is low in low shear and high in high shear. Remember, simple density or apparent density is the inverse of porosity. And this is a problem for high shear because high density reduces the deformability of the granules in the moment of the pressing in the tablet. So we need to control very, very carefully with the densification in high shear. It's the only problem that we can do, we can have in the high shear. The granule mechanical strength is low in low shear and high in high shear. The friability of the granules is high in low shear and low in high shear. The API segregability from granules is high to low in low shear and very low in high shear. This is cheap because the high forces that impellers makes into the granules, the API fixed to the granules and no move freely. But the distribution is regular to bad in low shear and ideal in high shear. This is a special question. The distribution of binder will impact in very attributes of the intermediate product. Finally, flowability and compactability two of the principal attributes we need to tablet in a high speed, is regular to good in low shear and very good in high shear. Well, it's obvious that the high shear process is best than the better than the low shear. Well, after this rapid overview of wet granulation, I want to say that technology is important, is very important, but it's not the only thing to take into account to achieve the quality and the productivity. The quality of the product and process efficiency depends on the technology, but beyond technology, they also depends of particular solution. We say quality and efficiency depends of technology, of raw material and formula, and the manufacturing process. It's important to pay attention in the raw material and formula, as well as in the manufacturing process. Many solutions are available to try to select the raw material, purchase specification, the composition of the formula, and formulation tips, expertise that we can give you, and the same for the process, manufacturing process. The configuration of production line must be the optimal, the process variable setting and the scale up could be performance, the specific application, methodological tips, and expertise are tools that we have to offer to you. And now I wanted to show you a case study that compares the low shear versus high shear. In this case, we use an example of taken from the scientific literature that show how the same formula product processed at high shear produces better compactability results. The granules obtained are good in flowability, but best compactability is obtained in high shear. This is the formula: acetaminophenol, lactose, and other common excipients, and water is the solvent. Here you have the citation. Well, now, granules produced by high shear and low shear, tablet and machine response. Here we show the graph of tablet hardness versus compaction force. This is the tablet hardness is the force we need to break the tablet, and the compaction force or pressure, if you want, is the force or pressure needed to form the tablet. Well, if we mark a defined value of tablet hardness, for example, here we put approach 15 kilopounds, what we note is that the low shear granulator, low shear granules, needs bigger force or pressure to form the tablet. This is 24 kilonewton versus 17 kilonewton, or in kilograms, 1,700 and 2,400. It's clearly that it's very high in the granules obtained by low shear. What impact has this increasing compaction force, increasing the pressure, will increase the wear of our tooling, the punches and the dies, and the machine components. So it's important question. We need to obtain granules with high compactability in order to need low pressure, low force to produce a tablet with high hardness, high mechanical strength. This is the very important question, and high shear with a high shear is possible to obtain. So the granules produced by high shear have greater compactability than those obtained by low shear. The reason is that due to the better distribution of the binder, because the impeller rotates at high speed, the binder involves the particles, the binder is very well distributed, and this impact directly in compactability. Well, at this point, I would like to give the word to Mauro. Mauro, are you here?
Hi, Arturo. Yes, I'm here. Thank you very much for this first part exposition. We have some questions from our webinar attendees we would like to answer. But before we go with them, please let me remind you that we have activated a survey on the screen that we highly appreciate you can answer. Yes, thank you. Now, Arturo, we have a question from Mr. Ahmad, who says, do we have parameters or equations to be considered for scalability?
Okay. Of course, the products are developed in the developed scale, of course, in very small equipment, and then the scaling up to the big ones in the industrial plant. Yes, exist many equations, many possibilities to do the scaling up. The typical equation is the tip speed constant. Tip speed is the speed or velocity of the point on the impeller around the base of the bowl. The tip speed is the revolution of the impeller times the diameter of the impeller. So if you use a MIC granulator of 10 liters and you use, for example, 200 RPMs, because the diameter of the impeller is reduced, well, when you scaling up to a MIC 200 liters with the diameter bigger, you will need to reduce the RPM in order to obtain the very similar tip speed. This concept, so, is the tip speed constant. Is one approximation. Another approximation could be the flow number constant. Flow number is a number that provides of chemical engineering.
I didn't understand.
This means flow number is the centrifugal force divided the gravity. So we have a formula that if we maintain constant the flow number in a scale, in a small scale, and the same value of flow number in the high scale, the probability to obtain a good, a similar quality of the granule is high. And finally, I say that the sweat volume is a very simple, because the sweat volume is the volume of granules that the impeller swept in each revolution, divided the time and the volume of the ball. These are simply 3 approximations, but it's very empirical, and we need to make experiments in order to adjust this scaling up procedure. But the most important are these.
Thank you very much, Arturo. We have another question from Helena. How can we avoid overweighting, overgranulation when using high shear mixer technology?
Oh, okay, it's a good question, this, because as I said before, high shear mixing has a risk of overgranulation, overweighting. The overweighting and overgranulation must be controlled by, first, to control the quantity of the solvent you add to the powders during the phase of wetting. This is the first. Control the quantity of water or alcohol or hydroalcoholic blend. The second is to control the speed of impeller. Put the eye here because the speed of impellers normally is high, and if use high speed, it's probable that you overgranulate the process, the granules. And the other control is not exceed in the time of granulation. So the end point, the optimal end point, the moment that we shut down the granulator, is very important, and we need to control not only volume, speed of impeller, and time of granulation. These 3 conditions are very, very important to control.
Thank you very much, Arturo, for these questions. Now we can proceed with the second part of this webinar, and please remember to complete the survey that we have on the screen. Yes, thank you very much.
Okay, thank you.
Sorry, Arturo, let me, excuse me, Arturo, I wanted to complement something. Very interesting what you are mentioning, Arturo, our response were very clear. Just I wanted to mention, maybe many of the people are present here in the group have experienced any problem with the compactability due to the different compaction force to be applied. I guess it's something that many people have experienced. Can you make more details on how we can avoid this kind of issues, since we say that trial and error are really not recommended, no? That's why you mentioned to make trials on small scale before scaling and applying tip speed and different equations to scale up, right?
Yes.
Well, thank you, Professor Vistalaya, for this first part exposition. There are some questions from our webinar attendees we would like to answer. Before we go with them, let me inform you that we activated a survey on the screen. We will appreciate if you can answer it. Okay, now let's continue with the question. The third is Mr. Oya. It is clear all are advantage on high shear versus low shear, except may be the risk of overweighting. Should we avoid that with training and avoiding trial and error?
Okay, Daniel. Yes, as we see, the high shear has a lot of of advantages over the low shear, but take care with the risk of densification and the risk of overweighting or overgranulation. These are the problems, but it's simply to avoid. It's simple to avoid if we control the critical variables of the process. Let's say impeller speed, the flow rate of the liquid binder, and the granulation time. These three critical variables controlled will avoid that we produce high densification and high overweighting or overgranulation. And the question is with training is possible and not with trial and error. Of course, we don't need trial and error because it's consuming time, material. No, we have to training the personnel, the operator, in order to they know the variables, how to modify and how to control the process and how to use the devices that give us the precise final endpoint. This will this question is possible to train the people, the operators, and avoid the problem. This is simply this.
Okay, many thanks, Doctor. Another question is, how can we avoid overweighting when using high shear mixing technology?
Avoid, let me repeat me?
Yes, how can we avoid overweighting when using high shear mixing technology?
Of course. Well, first of all, we have in the bowl a dry mixing and a homogeneous mixing of powder. The first step is homogenization. The second step is wetting. Well, the first question during wetting is to be in mind that the volume, the quantity of the solvent, water, alcohol, a blend of water, alcohol, the quantity must be controlled, because if you add an excess, of course, the probability of overweighting is potential, but it's not the only question. If you put a quantity of water, but you give too much time to granulation, it's possible that this water distribute around the mass and produce an overweighting because the excessive time of granulation at defined impeller speed. So what we to do is control the volume or quantity of water or solvent, control the impeller speed, and control the granulation time. We have to be near the machine, look in the monitor, and stop the machine in the precise moment.
Okay, well, moment. We have one question more. Is the question is from Muktak Madeha. How can granulation parameters scale up from late scale to production scale?
Okay. The products are developed in the small scale in the laboratory, and then pass to a step of pilot scale, and then to a production scale. These are the scaling in step: small, pilot, production. Well, for granulation, for wet granulation, we have a lot of equation or approximation approaches, say. The most common approach is to use the concept of tip speed constant. Tip speed is the question of tip speed is RPM times diameter. The multiplication of the revolution of the impeller multiplied by the diameter of the impeller. Of course, if we use a small ball, the diameter is low, so we need to use high RPM. Let's suppose that in this case, the tip speed give us 5 meters second. Let's say the end of the impeller rotate at 5 meters per second. Well, when we go to a bigger ball with impeller, for example, with the diameter bigger, what we can do is reduce the RPM in order to obtain the very same velocity speed, tip speed, let's say 5 meters second. Okay, so is the most common parameter in scaling up, the tip speed constant. There are another factor. For example, the From number. From number is a question that relates the centrifugal force. Impeller in the rotate produce a centrifugal force, of course. The centrifugal force that impellers make divided the gravity of the powders. This is the From number, has an equation, and so if we want to approach by the From number approach, well, what would have to do is obtain the very same value of From number at a small scale than in pilot or production scale. Approaches. And other very simple is the sweat volume. The sweat volume is the volume of powder that the impeller swept in each revolution, divided the time and divided the mixer volume. Well, if you can try to obtain the very similar sweat volume in a scale pilot that in a scale in a small scale. Maintain constant these three parameters could be a good form to reach high probability, high probability to a good scaling up.
Great. Many thanks, Professor. And I would like to inform to the attendees that we have left a survey on this platform. Please pay special attention in this issue because we look forward to receiving this survey completed by you. Okay?
In my opinion, we have to try with one of the approximation of scalability and to develop an experimental design of the trial. And in this case, we will obtain the best impeller speed. Impeller speed means the meters per second the point of the impeller move. So is 3 meters second the good? Is 5 meters second the move? Or is 8 meters second, the appropriate impeller speed. Well, this number in small scale emerge from experiment that we need to do, and ideally a design of the test is a facility to obtain rapidly and in less trials this figure, this number 3, 5, or 8. I don't know if I responded precisely your question. Gabriel.
Yes, perfectly. That was the idea. I'm sure that everybody experienced it once a time at least, problems with this of this kind.
Okay.
So very clear. Thank you, Arturo.
Thank you. Well, I continue with.
Thank you very much, Gabriel. Sorry, Arturo.
Yes.
First, this was Mr. Gabriel Porto from Ecovida. He's the Ecovida director. He's a pharmaceutical person with all pharmaceutical topics. Well, he was participating in this webinar. Arturo, we have one more question.
Yes.
It says the following: what methods can we use to compare of physical properties, mechanical strengths of granules, like freyability, hardness? It's a common case when granules obtained by different wet granulations have various mechanical properties. There could be more or less hard, for example. This is a question made by Helena.
Okay. Well, to compare the physical properties of the granules, physical properties, the mechanical strengths, the most common method is the friability. The very same method that we use with tablet, well, in the same equipment is used for granules. The methodology implies to weight X grams of granules, put into the friability machine, and put spheres of glass or spheres of steel. So then you produce the process of 100 revolution, and then wait again and calculate the loss of weight, and you will obtain a percentage of friability. And if this percentage is more than 20 or 30%, you can say, well, this granules is not has not sufficient or enough mechanical strength. This is for the granules. Of course, there are a lot of methodology, but this is a principle. I don't know if it's clear, Mauro.
Yes, thank you very much, Arturo. And then if we
Of
require
course.
further details, we can continue by emails, or we can coordinate another meeting with her. Thank
Okay.
you very much, and let's proceed with the second part.
Okay. Now we finished a very rapid overview of wet granulation. Now the second unit operation is the milling of granules. Normally the wet granules have a wide particle size distribution, you know. So we need to reduce this wide distribution of wet granules, and so we need to milling in order to narrow this distribution. And the milling can be done on the wet granules with a mill in line between the granulator here and the fluid bed dryer. As you can see here, and there is a mill, a wet mill. So the discharge of the wet granules pass through the conic mill, and the product enter to the fluid bed dryer. And another, or it can be done, the milling on the dry granules. So in this case, you use directly this. In order to clarify, I wanted to show you this. Milling of granules is, of course, it's a critical step that can define the quality of the semi-finished or intermediate product. And we have two methodologies, direct milling or indirect milling. Direct milling is what referred to wet milling. Wet milling, in line, granules, milling, and bed, fluid bed dryer. Drying at fluid bed, and then again, dry milling with another kind of conic hole. In the case you make indirect milling, well, you put the wet granules directly in the fluid bed dryer, and then when the granules are dry, you dry milling. These are the two possibilities, but now we will see the advantages of wet milling. In my opinion, wet milling is the best milling of granules. Let's see this. High shear wet granulation, wet milling. After this, we produce granules, small granules of homogeneous size that make easy to dry because increase the area, the superficial area, so the drying at the fluid bed is short, lower drying time, and very important, lower thermal stress, because lower time means lower thermal stress. And then, of course, you need to dry milling, and in this case, the lower residence times into the conic screen will produce lower percentage of fines. So this improves the flowability of the product obtained. Because these questions, this advantage, I guess, I believe that the wet milling is the most important process. Please pay attention the size of the holes. The size of the hole are bigger than the holes used in dry milling, because if you use a small hole to wet granules, will bust, and no, it's impossible to continue. Well, and now look at this disadvantages of post-dry milling. Mean wet granulation, drying the dryer, and then the milling. Well, high shear wet granulation, the wet granules go to the drying at fluid bed. So we have large and heterogeneous sized granules, not easy for drying. It's a very big problem in the pharmacy industry, because it's very common that during drying, the large granules is drying superficial, producing the phenomenon of case hardening. Mean this, for example, this sphere is dry in the surface, but very wet in the inner. So this is a problem, a common problem. And when you will to dry milling, you will have these problems. Increase the percentage of fines and will reduce the flowability. Increase the percentage of API not bound to granule, that promoting the API segregation. And of course, because you have high level of humidity here in the core of the big granules, this high humidity will bust the conic screen and will necessarily stop and clean. So clearly we have that the wet milling is better than dry milling. Well,
Arturo, excuse
yes.
me, sorry for interrupt you. I
Yes.
wanted to mention that really what you are mentioning is critical. Just an operation like a wet milling make a big difference on the finished product, really. So it's I think for all the people attending here, it's very important to consider that what you are mentioning right now. It makes a big change when you make it or not. Yeah? If you make this wet milling or you don't. So the result, let's say, in the next steps are critical. Right?
Yes.
So it's very important what you are mentioning. I take the time to say is to the people to take time for the survey. It's very important. We are putting the survey on the platform. So if you can answer, it would be very important to us. We can improve receiving your answers on the survey. Okay. Sorry, Arturo, it's your time.
Thank you, Gabriel. Well, now we need to overview the drying at fluid bed, the drying of a granule, of a wet granule. And so we will try theoretical and experimental consideration. First of all, I wanted to show you the static tray dry at the left and the fluid bed dry at the right. Of course, an essential technology change this time is necessary to have fluid bed dryer because have a lot of advantage. Here is a typical fluid bed dryer. It is a unit of Essica, industrial Essica from Pat Group. These are the configurable variables. You can configure air flow rate, inlet air temperature, and of course, the mode of modulation with the sensor in contact with the inlet air to the plenum or in contact with the granules fluidizing in the chamber. Two ways to modulation. Of course, you can monitoring airflow rate, inlet temperature, granule product temperature. This is very, very important, this one. And of course, you can monitoring the differential pressure across the bed or across the filter. And this gives you a lot of information. At the end of the webinar, I will show you an example of the use of differential pressure in order to define the optimal flow rate used in drying granules. Well, here is a comparison of the parameters between static tray and fluid bed. Rapidly, drying velocity in static tray is very low and very high in fluid bed. Fluid bed dries 10 to 20 times faster. Dry uniformity and drying efficiency is low in static tray and is high in fluid bed. Why? In fluid bed, the individual granules in motion expose more area for heat and mass solvent transfer. So this gives more uniformity and more efficiency. This is another question, very important. IPI migration segregation is high anesthetic tray and is null, is 0 at fluid bed. Why? Why? Because in a static bed, the solvent diffuse through the thickness that forms the granules at the tray and move part of the API like a chromatography, let's suppose, to the upper zones, generated API segregation, more concentrated in the upper part than the lower part. This not occur in fluid bed, so this is another advantage. Thermal stress is probable in static tray as improbable in fluid bed. Why? Because the lower drying kinetic at the static bed increase the interaction time of the granules with heat. Another question refers to the advantage in ergonomics. Is low ergonomic static tray and very high in the fluid bed. Loaded and unloaded the granule from the fluid bed is using vacuum transport, is simple, fast, ergonomic, etc. Facility required is big for the case of static tray and small for the blue fluid bed dryer. It's no common for this. Static charge, well, here take care. It's null, practically null in the case of static, and impossible in the fluid bed. So we have to be in mind in order to have the all safety devices to avoid any type of static charge. Process regulation is not easy to do in a static tray, and it's very easy, and we will see now an example, in the case of the fluid bed. The fluid bed drying process is highly adjustable physical process, which allows regulating the drying kinetic. And finally, process control drying endpoint. The endpoint is not easy to determine in the static tray, and it's very easy and very fast to detect the drying endpoint when we use a fluid bed. In fluidized bed, it's very easy to control the adiabatic equilibrium temperature and thus detect very precisely the final point of optimal drying. I will see you on a case study. But first of all, I want to show you that the monitoring through temperature of the granule. Here we have, this is the container where the granule, the wet granule is here. This is the expansion chamber. The air flows in this direction. And here we have a very, very important device. This is a thermometer, a thermocupla, that monitoring the temperature of the air that pass through the wet granulation. So the air enters to the fluid bed dryer at, let's suppose, 45 degrees, because you configure this temperature. But when pass through the granules, transfer heat and obtain evaporation of water and transport this water. So the temperature that this sensor in the chamber of expansion will measure is the equilibrium temperature of the drying process. And here is a theoretical aspect of the phases of the drying process. The phase one is the pre-warming of the equipment. But then, when the granules began to absorb the energy, absorb the heat, and deliver the water, the process entered in the phase 2. Phase 2 is the phase of maximum velocity of evaporation. So this step or this phase can explain 10, 20, or 30 minutes, and
I didn't understand that.
The temperature is constant, not move. But when the excess of the water or the solvent is removed, then the temperature of the air path that monitoring this device begins to increase. And this means that we are approaching to the end point. And so this increase is a signal to be an account, and the operator of the drying process have very well this phenomenon, because this phenomenon correlates very well, very well with the granules moisture content of the granules. Let me show you this. The phase 1, this is. The phase 2, in drying, in temperature, is the constant temperature, phase 2. What means the maximum velocity of loss of content. This is the phase 2. Here, the critical point is when the excedent of water, the superficial excedent of water was eliminated. The rest of excess of water is into the granules and will need bigger temperature to be removed. So this is why here the slope of the drying, the cinetic of the drying is lower and the temperature is increasing. So this means the following: temperatures of the granules measured with the device in the expansion chamber permits or allows to indirectly estimate the content moisture percentage of the granules and define the end point. And now here I wanted to show you a case study drying a fluid dry Nessica and a wet granule obtained in the MIC. Okay, here the objectives, well, are these: evaluate the evolution of the process, estimate the rate of grind, determine the endpoint, etc. Well, look at this. We have a formula, a typical placebo formulation of microcrystalline cellulose, lactose monohydrate, PVP, and these components in this proportion are mixing during 4 minutes in order to obtain a homogeneous dry mixing before wetting, of course. The condition could be, for example, for this size of ball, when 150 RPM and 1000 RPM of chopper. When we obtain the dry mixing homogeneous, now we need to take a sample to control the basal moisture content. Yes, in this case, the powder mix, this is 4.49% moisture content. Then moisture with water, for example, in this case, during 2 minutes at lower impeller speed and the same chopper, lower impeller speed and the same chopper, and After this, the third step of the granulation is the properly called granulation, 30 seconds at this condition. So 3 steps are made. First of all, drying, mixing, 4 minutes. Wetting during 2 minutes is the second step, and the third step is the granulation. Here we know that the endpoint, the very good endpoint, was 30 seconds of granulation, and then so we put in the fluid bed drying Essica to drying at this condition, 160 cubic meters per hour and 45 degrees in temperature of the air. Well, the result is stable, more or less 143 minutes last this process. You can see the inlet air temperature that maintain very, very close to 45 degrees. And then we monitoring the evolution of the granule temperature. This granule temperature is measured by this sensor I called is in the expansion camera. Well, and these are some, not much, but enough to have information, the content, the moisture content at different moment of the drying. Well, now here you have the graph. The graph presents the variation of the temperature of the inlet air and the temperature of the granules in the left axis. Here you have both the temperature of inlet and the temperature of the granules, the temperature measured by the thermocupla at the expansion camera. And the moisture content of the granules are at the right axis and is the blue curve. As you can see, the temperature of the air of drying is constant, 45 degrees. And this is the evolution in green, the evolution of the temperature of the granule. This is the flat excuse me. This is the flat period, the equilibrium temperature during which the vast majority of the solvent is evaporated. But when the vast majority, the superficial liquid is out, so temperature begins to increase and the slope of the content is lower too. So this simple experiment will give us the possibility to measure the endpoint temperature, in this case 34 degrees, and this endpoint temperature stop the process of drying. We took a sample and control LOD in a thermoscale and obtain the very similar content. So it's possible to determine the typical temperature of endpoint for each formulation. This is very important, I repeat. Each product, each composition have or will have the own endpoint temperature. This endpoint temperature will correspond to the precisely content of moisture of the granules. That really is the content of moisture before we wetting, of course. So it's very important to be in mind this kind of experiment. And in the industrial equipment, you only see the temperature. When you arrive to 34, stop the process, took the sample, and confirm the result. And the point and the process is finished. It's so simple that this. Well, another question is that the effect of drying airflow rate on the breakage of the granules, because if you use a very big flow rate, the impact the granules themselves or with the walls of the expansion camera or with the filters, well, this will produce increase in fines, and we don't want to be fines because more fines, less flowability. Well, this is an experiment made for us in this very small scale equipment, ESICA developer, in which we determine the percentage of retaining a different screen. And what we note with what observed is that bigger the airflow rate, bigger the percentage of the fines. So the pharmaceutical in the industry need to define the optimal flow rate, not put any flow rate. The flow rate must be configured, must be defined. What is the optimal flow rate for a defined formulation? It's impossible that all the formulations have the same optimal flow rate. So it's necessary to measure this. And here, I will show you a method. ESICA developer and ESICA industrial machine gives you the possibility to determine what is called the minimum fluidization airflow rate. In other words, the minimum airflow that moves the granules and fluidize. Well, this experiment is very simple. The red arrow describes the weight of the granule. The weight of the granules, gravity, no? The green arrows, the fluidization force, the air trying to oppose to the gravity. On the right, excuse me, on the left, you have the pressure difference across the granules bed. This is the difference. And the right, you have the height of the bed. Yes? So the measure of the minimum fluidization airflow rate involves increasing the airflow and monitoring the change in the pressure difference and in the height of the bed. Here, the airflow is expressed as B, meters per second, but the conversion is the same. And what we can see is this. With the early increase in velocity, in airflow or velocity, we observe that the pressure difference across the bed is increasing, but the bed height is constant because no fluidization is. This is a typical observation in this kind of function. At certain moment, an increase in the flow rate no longer increase the differential pressure, but increase the height of the bed. You can see this point of break is the minimum fluidization velocity or the minimum fluidization flow rate. So when we have this value, we have the minimum flow rate that fluidize our granules. You can then increase X%, 50%, 80%, 20%, depends the experience you will obtain that allow you dry efficiently, but without attrition or breakage of the granules that produce fine. This is a very important tool that ESICA have and you can use for optimize this airflow rate. Well, here I'm stop and wait for Mauro.
Hello, Arturo. Thank you very much for this second part of the exposition. It has been really, really interesting. Before we proceed with the further questions that we have from the people from the audience, I would like to remind you that we have the survey. If you still do not answer, please feel free to do it now. And also that the next webinar will be on June 7th. Yes, sorry, the third webinar will be in June 7th, and it will be the direct compression line. Okay. Now, going back to the questions, we have another question from Elena, and she says, "Thank you very much for answering about the mechanical properties of granules. I understand about friability methods described in EP USP, but what about hardness or strength? Does it use for granules estimations?" If you can please, Arturo, proceed with answer for her question.
The hardness, the mechanical strength of a tablet is the force or the pressure that we need to break radially the tablet. This is the definition of hardness or tensile strength of the tablet. But this tensile strength, this hardness, of course, that depends of two aspects: the compactability of the intermediate product and the pressure we put in the moment of the tableting. This is the aspect of the is the way in the or the dependence of the hardness. Hardness depends of the compactability and the pressure. If the compactability of the intermediate product is high, you will need low pressure to obtain a high hardness or high strength. If the compactability is low, you will need high pressure to obtain a tablet with high hardness or tensile strength. I don't know if Elena, I respond precisely her question, let me know, please.
Okay, yes, for my part, I think it has been really clear. Now, due a matter of time, we are also 15 minutes delayed, but we hope we got many questions, really interesting questions that it was nice to share with the rest of the people that joined us. We didn't want to avoid making for everyone, but
Sure.
we will
If you
also
have any
answer by
other
email,
questions,
more
yeah.
questions.
Mhm.
Yes, definitely.
Sorry, Mauro. I was saying that if you have, we have more questions, but because of time, those will be answered, no, directly to the
Yes.
people.
Yes, by email.
Okay.
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 Well, I would like to remind you the next webinar, it will be direct compression line on June 7th. We will share with you the invitation during the following days. Also, we will share with you this presentation, today's presentation. And also, we will have today also the webinar from the first edition will be in our YouTube channel. So you can see it again also. And this webinar, we will also have it on YouTube on the next 10, 12 days. Yes. Now, thank you everyone for participating on this webinar. And it has been really a pleasure to have you back. And well, hope to see you next edition. And have a nice day.